ظبطت. Hello. So, how many are we? 12. Good job. Yeah, okay, so we'll talk about the pipeline we used. Okay. Yeah, okay. Okay, okay, so we'll talk about a little bit about the pipeline we used at the Romanian Nationals, and also about a little bit about the 9-sample Auton. Right, so the pipeline basically was a dual target system. It basically selected one primary target and then tried to find a secondary target, which was selected in case the first one was bad. Okay, so let's go a little bit through how it worked. So this is the overview. Right, so it detected the targets, it computed some targeting offsets, just like the Limelight TX and TY, which was calculated, by the Limelight formula, the FOV and the resolution, right, which gave you the pixel coordinate in the degrees. Then it also highlighted them so that we could debug easier, and then it also supported red and blue. In case that there were no more yellow ones to collect, it would collect the align-specific ones. Okay. Yeah. So it used an HSV color threshold, right? As you can see, the red one was a wraparound one because red is at both edges of the HSV color range, so that we could detect them better, right? So, and we also, it extracted the contours. Just a second. Okay, so this is the summary of the pipeline. And then next is how we moved the intake, right, the turret with the extender with the claw to be above the sample, right, the contour that was selected. So we actually used inverse kinematics, and what it did is that it took an input in millimeters, which was kind of like the distance the end effector needed to be, which is the claw, relative to the robot chassis. So imagine you have like a local coordinate system glued to the robot, it rotates with the robot, and that's basically how we control the turret. And then after calculating the extendo extension in millimeters and the turret angle in radians, it would just feed those into the intake subsystem, and the intake subsystem would like pass some checks, right, some safety checks. And then if everything was all right, then it would go ahead and collect that sample. Now, how do we make it so that the output from the pipeline could, how does that output from like TX, TY in degrees somehow end up as millimeters for the inverse kinematics, right? So that's where we used a lookup table, right? A lookup table with Delaunay triangulation. What it is that, as we all know, a lookup table takes an input and it gives you an output, right? And what the triangulation does is that if you give it an input that it doesn't have a saved output for, it would sort of estimate for you an output, right? And what the lookup table did is that it calculated the output, it would give it into the intake inverse kinematics, and then the claw would reach above the sample, and also the claw angle was given by the pipeline, the angle the pipeline detected, and also the turret's angle, because if you rotate the turret a little bit, then the claw would also be angled, right? So you had to remove that angle from the turret. Okay, now how do we calibrate this lookup table? So we had two options. Either we generally just put the sample on the field, we saw what the pipeline detected as the positions, and we also manually put the intake position in millimeters, and then we just save that in the lookup table, right? We have like a long list. For nationals we had like 250 positions saved. And then we also tried another method. We just placed April tags on the ground, and then basically based on those April tags it would automatically know how to what the intake positions were for each one of them, right? This is like an example that was used for a calibration. This isn't the exact one because we couldn't find it in the workshop, but this is just like an example of how it would look like, but they would be more spaced out. Okay, now some questions, if anybody has some. We'll wait a little bit if anybody has some questions. Putem să închidem dacă nu are nimeni. Nu? Da, ok. Okay, if nobody has questions, then I guess we'll end the live stream. If you, oh, okay, yeah, okay. Just now they started popping up. So where's the camera positioned on our robot? So it's actually positioned in front of the robot, right next to the turret, right, like really high up, right at the size limit, right, like at 45 centimeters. And it's slightly angled down, so like this angle, it's about a 40-degree angle, and it can detect the samples quite well. It can see from one end to the sub to the other end of the sub, and it's also cannot see above the like low specimen bar, right? You can go directly above it. And is there any way you can go into detail in optimizing recognition features with the Limelight? Yeah, I can give you a few tips that helped us. So first of all, before doing anything, right, with the pipeline, any sort of processing, you should be sure that your actual like input, right, the thing that the Limelight detects, the video is actually okay. You should make sure the exposure is well, so that it's clearly lit up. You could also play with the sensor gain. We have sensor gain turned up, not really that much, but we do use it. You can also use the black level offset if that helps you. For us personally, it didn't really do anything that good for the pipeline. And then for calibration, you just really have to go step by step in the process, right? First of all, you have, for everything to work well, you have to make sure that every step is well calibrated, right? So you can't go and expect some really good contours to be given by the Limelight if your HSV threshold, right, your mask isn't well calibrated. What the lookup table is, we haven't heard about that. Yeah, so you can just search it up online. It's quite used. Basically what it does is, imagine you have kind of like a dictionary in which you give it a value and it returns a value, right? So if, for example, for each animal that you gave it, it would return a number. You could say that you give it the animal dog and it returned 5, for example. And we use that and basically we give it the pixel, the tx and ty of the sample, right, which is the pixel coordinates slightly wrapped around like the camera FOV and resolution. And then we give it that and it returns the distance of the sample relative to the robot's chassis, which is then fed into the intake inverse kinematics. Are you guys going to make the code open source? Not right now, but maybe after the championship, right? We actually use a custom motion planning library, which is called Flex Motion, which is set to be open source and released just like Pedro Pathing or Roadrunner, but it is currently still heavily under development and it's really not user friendly. It kind of only works because the people who made it are the people who are using it, so they know every nook and cranny of it. But yeah, it's really not well documented and it's really not user friendly, so that's why it's still not open source. And yeah, based on the optimizing recognition features, after you detect the, after you apply the threshold, you could also do some morphology, right, so that you can sort of delete small specks, and maybe if samples are slightly touching, after the morphology, maybe they don't touch, right? Do you have any suggestions on optimizing the claw system? We have, but what is the best way to deal with the fact that samples are close to each other and when the claw goes down it might hit the other sample? Well, you can simply, instead of trying to collect a sample that is close to other samples, you can try and target another sample which is kind of like alone, right? And you can also just generally optimize the claw itself, right? We went through a lot of claw iterations and our claw actually has quite a large margin, and it also collects samples which are close to one another, right? Like if there's like 2 samples and it's above 1, then it will collect that one, it won't have problems. And then sometimes even if there are 3 lined up one next to another, depending on how the claw pushes itself into the sample, it can collect the middle one. How do we manage to use Flex Motion if it is still under development? Well, it is in a working phase, right? Like it does work, right? You have the Bezier curves, we have the trajectories, we have the motion planning, we have the heading interpolation, we have all of those fancy stuff. But the idea is that it's really wonky to use currently. It's not like Pedro Pathing or like Roadrunner, which have clearly well-defined tuning process and documentations. Flex Motion is kind of like you can do everything and anything you want, but I won't hold your hand. And like if something goes wrong, if you don't know every little step that it calculates, then you won't know what's the problem, right? Was inverse kinematics hard to implement? Well, not necessarily. Basically what it does is that you can think of it as having a circle, right, which is the radius of the turret, which can move up and down on a linear axis, which is the extendo. And you just have to find the points that basically you have to find the point that can exist on the circle, and if the circle can intersect that point and the center of the circle can also intersect the line, then that means that it is a valid point, and you can translate those values into the real life like real life values for the extender and the turret angle. And you will also have two solutions for this, because for example, if your point is here, your turret can sit like this or it can sit like this, and you can sort those based on whichever one you want. We usually like the one which is with the least extendo extension, right, because it's just faster to reach it that way. But if your claw or your turret works differently, then maybe you could want to choose the one where the extendo is extended way more and the turret is angled downwards in a way, like backwards. Is flex motion more like point to point? Well, it does have point to point capabilities, but that's not really what it is for. That was a really like flex motion was point to point like a year ago in center stage. But now it really isn't point to point. You can use it as point to point, but it's more about Bezier curves, it's more about interpolation, it's more about controlling your orientation based on specific conditions. It's more about using the velocity of the robot, right, certain derivatives to make sure that everything goes well, and to not use like time as an important part of your auton, right? That's another important part about flex motion. It doesn't have conditions that are controlled by time. It's not like you reach a position and then you wait half a second and then you drop the sample. It has other conditions that it needs to accomplish, right? What is the best angle the camera should be at? Well, I believe that the camera should be angled top down, so that when you see the samples, they are clearly separated. Because if it is at an angle, then if you have a lot of samples of the same color, then you will kind of see them like a weird straight line, because you're seeing it from the horizon. While if you're seeing it from top down, then you will see them clearly separated. And it's also easier to do the conversion from the pixel coordinates to like an intake, to the intake coordinate system, right? And yeah, we do activate the Limelight at the start of auton, and we keep it activated all the way. We found that there's a little bit of a latency, like a delay. If you keep turning it on and off, it just kind of helps us to keep it always on. Because our pipeline really doesn't use many resources. It's like a 25 FPS, 20 FPS at 920 by 740, right? So it doesn't really have problems with the processing power and it overheating like with machine learning algorithms, which we try to use, but way too little FPS for us. We would have to sit too much, right? Sit still too much, and wait for the Limelight to catch up. So advice on the adjustment of the claw. Well, I'd say that the three biggest factors would be making sure that the contour is properly detected, right? Because if, for example, it detects only half of the sample, then the angle might be off. The second most important part would be to make sure that your claw angle, right, when you give it an angle of 25 degrees, make sure that it is actually at 25 degrees. Then the third biggest would be if your Limelight is at an angle and it's not directly parallel with the claw axis, right, then you have to subtract that angle from the detection. But I'd say that if you make sure that your contour is detected well and that your claw actually moves to the angle you give it, then it should be alright. It helps by we tuned that by just making another pipeline which returned only the angle, keeping the claw on, and then moving the sample, right, and in real time it would rotate, so that way we could tune it to be well. Though we didn't really have to tune a lot because we just made it so that the claw would always sit at the angle you gave it, then made sure that the pipeline gave you the correct angle in degrees or radians, whichever you prefer. You just have to make sure that you're converting it and not, for example, accidentally feeding degrees into your claw, which actually needs a radian input. How do we separate adjacent touching samples? Well, you see, at the Nationals we didn't have any sort of filter or algorithm which did that. So what we did was that we just ignored those samples, right? If there were samples touching, we just said, okay, ignore those. Either go into your emergency sequence, either go for your secondary sample, right, the secondary contour, right? It would have to bypass a lot of filters to actually make it to the intake and to the intaking sequence. But yeah, we just ignored them. What's one piece of advice you can give to someone that just started to use Limelight? Well, make it simple. Don't start with like crazy turrets, claws, rotating stuff. And use the beginner pipeline, right? The HSV color threshold that you're given by default by the pipeline works great, right? If you position your Limelight well, and if you have, for example, an active intake, then it shouldn't be hard to program a good autonomous. Not like a crazy, like 15 sample one, but just like a good 7, 6 sample auton would be quite okay, right? And not that hard to program with the default pipeline. How you reduce this consumption of resources or energy so that your robot doesn't disconnect mid-match? Well, we don't really have any problems with that, honestly. During the teleop, the Limelight is, the pipeline of the Limelight is turned off, right? It only gets started during the auton, and it only is turned on during those 30 seconds, because during the teleop we don't actually use the Limelight. It is all driver control, or like driver, like the secondary driver maybe tunes some things during the match. But yeah, like I said before, the pipeline really doesn't use that many resources. We try to keep it as primitive as possible, because if we saw that when we made the pipeline too complex, then some slight changes to the environment would cause some thresholds, some filters to not work correctly. We just found out that we could just keep it really simple, make it work really fast, really well, and then just do well with that. What suggestion do you have for the code if the sample is far from the claw and the robot itself has to move? We feel sometimes the robot doesn't move accurately enough, and that causes the claw to move, to miss. Well, I'd have to say that you should first make sure that your chassis is properly tuned, right? To make sure that when you give it a position, it actually goes to that position. Like an error margin we like to aim for is 2 millimeters, right? Because when you have that, and that's for like a well, like the 2 millimeters is the smallest error we like to give it, because during auton we just give it like way larger thresholds depending on what it does, right? And if you know that your chassis moves well, then you can generally just calibrate it so that if your contouring works well and it returns stable values, then you just have to play with scalars, right, multipliers, maybe some offsets even if you need those, right? You just have to make, you just have to take it step by step and make sure it works well. And maybe even some delays can be added. For example, the robot tends to overshoot, and maybe that moves the claw. some sort of way, then maybe adding some sort of stable delay could also help. But then again, I don't have that much experience with auto-collecting with the chassis. We only had like a 6 sample auton during the regionals, which used the chassis, and that again was made with the Delaunay triangulation lookup table, though it isn't like a necessary step or even a good one. It is actually kind of like the competition is in like 4 days, it needs to work, it doesn't work, what do? I just like hard force the solution. That's basically what the lookup table is, right? And maybe if I imagine your claw is on an extendo, right? So maybe you can have some checks. If you see that the target is too far away for the extendo to grab, you can make that difference, right, between the target and the maximum extendo. You can get that difference and feed it into the chassis, and so then both of them will move forward to grab the sample. Though I don't know what your robot does, so I can't really accurately give you some tips. Yeah, we will post our nationals pipeline to be open source. Any open source material you suggest we look at? Well, good question. I mean, if we're talking about the pipeline, I mainly used like the Wikipedia and ChatGPT to explain concepts to me. But if we're talking about like generally controlling the chassis, like tuning values, converting from like relative coordinate systems to global coordinate systems, I would look at, for example, Control-Alt-FTC, maybe even the controls engineering document. Right, the documentation is like a 400-page long documentation with control engineering for RFC. I will post it on the Discord if you guys want to. And also like maybe a little bit of math, right? A little bit of analytical geometry, a little bit of matrices, right? Like a rotation matrix, some polar coordinates. If you guys want to, can I just ChatGPT to make me some code? Yeah, you could, but most of the time it wouldn't really work that well. You will still have to tune some values. You will still have to understand how it works, like how the code works, to make sure that if something goes wrong or if something doesn't work, you know where to look and you know how to properly tune values. Because yes, you can tell ChatGPT to make your code, but you need to understand it to have it properly tuned and have it properly work and be fast and reliable. Okay, so if there's any more questions, you can ask any of our members in the Discord server, right? The unofficial FTC Discord server. We most of us have the 17861 Team CSH in your name, so you can just search that up. You can find the member and you can just write to them. Though we won't talk about our championship pipeline, that we will talk about that after the World's Championship, but if it's anything about our nationals or regionals pipeline, then we're glad to tell you anything about it. Okay.